So with this video, we start asking the very important question about goodness of fit of a linear model. So far we have learned that given a particular form of the linear model, that is given a design matrix, how to find out the best estimator beta and for sigma square hat. But the question is whether even this best estimator is good enough or not. Now naturally your first expectation would be to have some measure such that once you have fitted the model, you will compute that measure, something like an ideal number, and you will compare it against a threshold. If that number exceeds that threshold, you will say yes, it's a good fit. If it is below the threshold, then you will say it's a bad fit, or the other way around. If it is less, then it is good, and if it is more, it is bad, whatever. Unfortunately, this dream is never to be fulfilled. You can never capture the nuance of a linear model in terms of a single summary statistic. You cannot just compute a single number and based on that judge whether that is a good fit or a bad fit. The best technique always remains to look at the residuals, the residual vector. When we say that we want to look at the residuals, we mean plotting the residuals against whatever comes to our mind. We might plot them according to the order of observation, that is, if the ith residual is called EI, I can plot the EIs against the I's, or we may plot them against some covariate, or we may plot them against any factor input that we have. And whenever you make any plot of the residuals, make sure that you draw the zero line, the horizontal line through zero. The ideal situation that you will get, you should get, something that should make you happy, when you are plotting the residuals either against the observation number or against any covariate, should be like this. Here you can see that all the points are more or less patternlessly scattered symmetrically around the horizontal line through zero. That is the desired thing. Any departure from this and you should suspect that your model is not a good fit. Of course, you should also make sure that these points are not too far away from zero, in which case you are having very large error. But the main idea is that you should not have any systematic departure from zero. Even if you have some large departure from zero, that is possibly allowable, but no systematic departure from zero. That is the more important thing. So if you have something like this, you should be happy. Now if you are plotting it against some factor input, in that case you will have a plot like this where against each factor, or it could be a factor combination, you will have a scatter plot, you will have a box plot, and all these box plots should be more or less centered around the zero line, and they should have amount of scatter similar. If they have different scatters, then you suspect that homoscedasticity is not a good assumption. Now let's take a look at a few situations where things might go wrong. So if you see these things, then you should be skeptical. Suppose you see a situation like this where all the residuals are more or less above the zero line. So they are not symmetrically around zero. If you see this, then you immediately suspect that you should put an intercept term. This will happen only when there is no intercept term in your model. You should rectify it by putting that intercept term. This is when you are plotting it against observation order or against some covariate. If you are doing the same thing against some factor input, in that case you might get something like this, where all the boxes are either consistently below or consistently above the horizontal line through zero. This also suggests that you should include the intercept term. Now here is another situation where you see something like this. This is the situation that was seen by Adrita or by Rajdeep when they did that project 1. You see that there is a systematic departure from zero. On an average, they are against zero, but Initially they are more positive, then the residuals are negative, then the residuals are positive again. This systematic departure is typically seen when you are working with a regression setup. This is a continuous thing, covariate, possibly including higher powers of that covariate is going to solve the problem, as in case of that project 1, including a cubic term solve the problem. But of course you must make sure that including that higher power term is really justified in terms of the domain of the problem. If you are seeing this where this is the observation order, then you have to be careful. So these observations are most likely not IID. There is something which is changing over time. So when you are taking the first few measurements, you have done error in the positive direction. When you are taking the middle measurements, you have done an error in the negative direction. So possibly you are having a time series effect somewhere in your setup. So you have to think carefully about that. Now you might say something like this. If you see a pattern like this, that indicates that you are having heteroscedasticity. So things having a fanning out effect or a fanning in effect, depending on how you look at it. And there are various ways by which you can tackle it, namely by going into what is called generalized least squares and etc. We will discuss those things later, but for the time being, you should watch out for a pattern like this. Of course, you can see a similar pattern if you make a box plot against a factor input. In that case, you will see some box which is tall and some other boxes which are thin. All of them are centered more or less around 0, but this indicates that you have possible heteroscedasticity. Now, it is quite possible that you have more than one such problem occurring simultaneously. Then you have to again deal with it accordingly. For the time being, I am merely saying what indicates that something has gone wrong. Now, how exactly you tackle those things, we will come to that later, but here we are just coming to the thing whether we can say that it is a good fit or not. Now, here is one situation that often occurs in real life where you have an outlier. All these points, all these residuals behave more or less nicely. Here you have one point which is an outlier. Now you start thinking whether I should ignore it because it's just one point, or I should just throw away my model. The general technique should be to not to throw away your model, but look at that particular case more carefully. It often turns out that that has some special feature which will possibly open up a new area of research. So finding the reason behind why that is an outlier might be the most important part of that particular report, statistical report. So these are the various ways by which you can detect lack of fit of your model by looking at the residual plot. And this is by all means the most important way by which you can detect lack of fit.